Welcome again to a new lecture. This is lecture number 27 of phase equilibria course. So we will first do a recap of last lecture. So in the last lecture we looked at phase diagrams of phase diagram of PVSN system. PVSN is basically eutectic, binary eutectic system, and PVSN is basically important material because it is used as a soldering material. And the reason why it is used as a soldering material is because it has a eutectic phase diagram in which, so you have lead and then you have tin, okay, and then there is a eutectic at about 170 degrees centigrade which allows it to melt at lower temperature than its constituents. So it is at 61.9%. So this is lead, this is tin, this temperature, and what you have here is at about 183. So this is 183 degrees centigrade at 61.9%. Lead, it makes a eutectic where liquid actually transforms to alpha and beta phase eutectic mixture. So this has lower melting point than either of the constituents. As a result, it fulfills the requirement of a solder to melt at lower temperature and solidify quickly. It does not have broad solidification regime. So PVSN solder of eutectic composition so it has following attributes. Number 1, lower melting point, and 2, it has it solidifies at a fixed temperature. So as a result, it does not have and does not have a liquid plus solid zone. Now liquid plus solid zone is avoided in welding because you do not want your weld to be mushy. You want your weld to solidify quickly so that the parts are retained, so the parts are integrated fast. So as a result, we prefer lead tin alloy of eutectic composition for soldering. However, we looked at microstructural evolution in various regimes. So we chose 3 regimes. One is the eutectic hypoeutectic regime, second is eutectic regime, third is the hypereutectic regime. And when we look at the microstructure, so in the hypoeutectic regime, you had these crystals of proeutectic phase of alpha. So this is proeutectic alpha, okay, and this is surrounded by these beta phase this is surrounded by the eutectic which has a lamellar structure like this. So this is alpha plus beta eutectic, and this is proeutectic alpha. So here the proeutectic alpha is the lead rich phase, and the alpha plus beta is the eutectic, which again consists of alpha and beta, but presence of alpha in 2 different forms makes a distinction between the 2 alphas. And then we had this eutectic composition. For eutectic composition, you get a microstructure which is basically a lamellar microstructure. So you have had a lamellar microstructure. So this is only alpha plus beta eutectic. And then third composition that we took was this hypereutectic composition, for which we had crystals of let us say beta, okay, and these proeutectic beta. So this is proeutectic beta, and this is surrounded by your eutectic mixture of alpha and beta. So, this is alpha plus beta eutectic. So, again you have two different forms of beta, one is the beta in proeutectic form, second is the beta in the eutectic form. Both of them will have same composition, but their morphology is different. So, these are the microstructures that we were looking at, and then we looked at iron carbon phase diagram. So, that is what we will continue in this lecture with as well. So, let me draw the iron carbon phase diagram. So, this is iron carbon, or it is also called as iron cementite phase diagram. Cementite is a metastable phase, so that is why it is normally referred as iron carbon phase diagram, because carbon is the more stable phase of the two. So, let us say I have, so this is 0% carbon, this is 6.67% carbon. So, if I now divide this, this is 1, 2, okay. So, this is the phase diagram of, so this is 1, 2, 3, 4, 5, 6. Let me do one thing, let me just truncate, let me just expand on this side and contract on that side. So, let me just make it 0.5, 1, 1.5, 2, and then let me put a break here and let 6 directly come there. Okay. So, let me just so this is 0.5, 1, 1.5, 2, and then I put a break here and then directly I go to 6. Okay. And let us say temperature wise we are at, so this is this would be your roughly 1600 degree centigrade. So, this is where we would be at about 800, and this would be roughly 400, and this would be approximately 1200 degree centigrade. So, if I now go about plotting this, so first I draw at 727 degree centigrade. So, this is 600, 700, somewhere here. So, I start from like this and I go up to all the way this point. So, this point is 0.022, and then I connect this to, so this is 1900, so roughly here, and then this goes down there, and then I draw a line at 0.8. So, 0.8 is this, so that would be roughly 0.8, right, and then I draw, so this is 0.022, then I have somewhere here 1493, so this is 1400, and somewhere here I have a peritectic region line. Okay, so this is 0.1, this is 0.15 nearly, and this is about 0.5. So, let me just connect these 3 points, right. So, let me just connect these regions. So, there may be some error, but by and large it should be all right. And then we have 4.2 somewhere here. So, this is 4.2%. So, what I do is that I connect this point with that point and this point with this point, and then I have a daughter region. So, this is liquid phase all about, this is liquid plus delta, this is delta, this is gamma, this is liquid plus gamma, this is gamma plus delta. So, this point is 0.1, this point is 0.15, this is 0.5. These are approximate numbers. Okay, so they vary between books as well. This is no, I'm sorry, just I made a mistake here. This line, there should be a line at 1200 and 1147, which should be somewhere here. So this is 1000, 1100, so somewhere here I will have a line. Okay, so this will start at about 2%. So this line will start at about 2%, and it will go all the way up to this point. So yeah, so this is what I will have a phase boundary. All right, and then 4.2 will be here, so I can remove this 4 point from, oops, okay. So I have this as that. Okay, now it is better. So liquid, this is liquid plus gamma, and this is liquid plus Fe3C. Some people also write graphite, and here you have a mixture of gamma plus Fe3C. Here you have gamma, and this is gamma plus alpha, this is alpha, this is alpha plus Fe3C. So it's, according to this phase diagram, up to 2% what we have is steel, and beyond 2% what we have is cast iron. Okay. Now there are a few things that we need to know. We have looked at a few microstructures of this. We know that this is a eutectoid reaction, this is a eutectic reaction, and this is a peritectic reaction. We also know how these reactions takes place. Now about this phase diagram, you can get a lot of information from this phase diagrams. First is alpha goes through a transition in the pure state at 910 degree centigrade from alpha to gamma phase, and this transformation, so at 900 degree centigrade, alpha Fe transforms to gamma Fe. So this is BCC alpha transforming to FCC gamma upon heating. Okay, and then at high temperature this gamma, so this is about pure iron. Okay, so at 1394 degree centigrade, your gamma Fe transforms to delta Fe at 1394 degree centigrade upon heating. So this is the transformation, allotropic transformations. So these are called as allotropic transformations, which occur when you heat pure iron as from room temperature to high temperatures. So this gamma Fe is again FCC and delta Fe is again BCC. So these are the transformations that occur in iron. Now when you look at other aspects of this phase diagram, what you see is that the most important part of this, so there are two important aspects of this phase diagram. First is the steel, then second is cast iron. So steel, so for iron with carbon less than 2% is called as a steel, and when carbon is 0.0 to 0.8%, then it is called as hypoeutectoid. So let me write it in a different way. So carbon is less than 0.8%, greater than 0, it's called as hypoeutectoid. Carbon being equal to 0.8%, it's called as eutectoid steel, and carbon being greater than 0.8% to 2% is called as hyper-eutectoid steel. In general, steel is used in compositions which are of hypoeutectoid or eutectoid steel, because when you go to hyper-eutectoid steel, you have steel becomes very hard. There are three phases that we generally consider in transformations in steel. First is the high temperature phase, gamma Fe, which is called as austenite, which has FCC structure and it has high solid solubility of carbon in iron at about 2% at 1147 degree centigrade. Okay, and the solid solubility of iron in carbon in gamma Fe goes down this line. So this is 2%, this is 0.8%. So this goes down as you decrease the temperature from 2% to 0.8%. Then we have so this is first. Second phase that we have in this phase diagram is alpha Fe, which is low temperature phase, and it is known as ferrite. Ferrite is BCC structured. It's the solid solubility of steel carbon in ferrite is about 0.022 or 0.025%. So it's about 0.02%, and this is at eutectoid temperature, which is 727 degree centigrade, and this goes down to roughly 0.008% at room temperature. So virtually pure iron does not consist of any carbon in it at low temperature, but whatever carbon it possesses, it is sufficient to provide it higher strength as compared to absolutely pure iron. And third phase that we have available is cementite, which is a line compound, and this so it's a intermetallic or line compound. It is harder than alpha Fe or gamma Fe. It has nearly fixed composition. I think it has fixed composition, let us not say nearly fixed composition, and it is a metastable phase. So if you provide appropriate conditions to steel, it happens not in steel as such, but it happens more in cast iron. When the carbon percentage is higher, it tends to decompose into, so Fe3C tends to decompose into Fe plus C, and the C is nothing but graphite, and this happens at higher carbon concentration, silicon concentration, or slow cooling conditions. So it is very much a reality in cast irons. So the first phase, so this is where now it is the mixture of these phases, the morphology of phases, which determines the properties of a steel, and this is why understanding of phase diagram of steel is extremely important. So let us just focus on the phase diagram of steel as of now. So let us draw the particular portion consisting of so let us say we are up to about 2%, and this is 0.8%, this is 0.02%, okay, this is percentage carbon. So there are three compositions which are of importance. The first are the compositions which are of carbon less than 0.8%, second is the composition which is of 0.8%, and third is the composition which is greater than 0.8%. So the microstructure that develops here, so last time I showed you what the microstructure is of eutectoid steel. So what happens here is you have, so if you start from eutectoid steel, so up to this point you have a microstructure which is like this. You have grains of gamma, so this is gamma FCC phase, and the moment you cross this temperature just below eutectoid temperature, the microstructure transforms to So this is called as lamellar mixture of alpha Fe and Fe3C. So of course, since the carbon is very small, alpha Fe proportion is that alpha thickness of alpha Fe plates is much higher as compared to cementite plates, and this mixture is called as perlite. And the microstructure in reality, as I showed also last time, it looks something like this. So this is what the paralytic microstructure looks like. Okay, so we have these, you can see that these are the plates that you have here. So these are the alternating plates of alpha Fe and Fe3C, and thicker plates will be that of alpha Fe and the thinner plates will be that of cementite. And you can see that you have colonies. So this is one colony, then you have another colony here, then you have another colony here, then you have another colony here, you can see, and then you have another colony here. So you can see the boundaries between the colonies quite clearly in an optical microscope, and so on and so forth. So you can see that these are different perlite colonies. And how do they grow these perlite colonies? So what happens is basically you start from so you have a microstructure in which you have these gamma grains. Okay, so I'll just draw these 3 grains. Originally it was gamma, and at the grain boundaries of gamma you have the sudden growth of these 2 plates. So these plates grow in this fashion. And they grow quite fast. Since they grow quite fast, the growth is, there is not much growth. As a result, the feature size is fairly small. So if you go to the micrograph, you can see that although the length of these is about, so this is nearly 2 micron marker. So this is roughly 10 micron by 10 micron area. So this is roughly 10 micron by 10 micron area, but you can see that within this 10 micron you have nearly about 50 or 50 to 70 plates. So each of them is extremely thin. So if this is the thickness of this, so this is the thickness of, let's say, 2 plates. So this is nearly approximately equal to this, which is about about 1/5 of 2 micron, which is, so it's about half a micron, a quarter of a micron. So this is about quarter of a micron, and you can see that each of these lamellas is less than, it's about 0.1 micron. 0.1 micron is about 100 nanometers. So these are very, very thin plates. So you can have thin lamellas of alpha Fe and Fe3C. So if alpha Fe is thicker, Fe3C is going to be even thinner. So as a result, you have this. So you can control the thickness of these by controlling the cooling rate, the rate at which steel is cooled, so that you can change the amount of time that is needed for solute partitioning and the growth of these phases. So generally, as you can probably see in phase transformations, but generally as cooling rate decreases, size of features increase, cooling rate decreases, size of, so slow cooling results in a coarser microstructure, and as a result the coarser plates of ferrite and cementite, and this has profound influence on mechanical properties. So the finer perlite gives you higher strength. So fine perlite, so microstructure consisting of fine perlite results in high strength, high hardness, whereas coarse perlite results in higher, I can say, and coarse pearlite is lower for a given composition. So, lower sigma and hardness. Okay. So, these are the relations of size of features which are not predicted by phase diagram, but which are related to kinetics of phase transformation, which is out of purview of this course. Now, the third, so this is the phase diagram, this is the phase evolution or microstructure evolution for 0.8% carbon steel, and similarly you can go about now as you go, the transformation is complete at this point. So, as you just cool from here to here to from 727 to lower temperatures, nothing much happens in terms of phase evolution. The phases remain the same as you lower the temperature, and you can determine their phase fractions by applying lever rule. So, if you calculate the phase fraction at this point and the phase fraction at very low point, it is not going to change much, because you can see the solid solubility changes from 0.02% to nearly 0.008%. So, 0.02% itself is quite low. So, the reduction, so you can calculate actually. So, we can calculate percentage of alpha Fe in eutectoid steel. So, at Te minus, that is just below 727 degrees centigrade. So, this alpha percentage alpha Fe would be equal to 6.67 minus 0.8 divided by 6.67 minus 0.025, and at room temperature percentage alpha Fe would be, so this is into 100, 6.67 minus 0.8 divided by 6.67 minus 0.008 into 100. So, you can see that if I do a quick calculation, this is 6.67 minus 0.8 divided by 6.67 minus 0.025, and this is about 88%. Okay, and if I make a change in the values there, 0.008, this also leads to about roughly 88.1%, this was about 88.3%. So, it does not change much. So, when you come from temperature just below eutectoid to room temperature, the percentage ferrite remains nearly the same, because there is a very little change in the solid solubility of alpha ferrite. So, what we will do in the next lecture is we will look at the microstructure evolution for hypo and hyper eutectoid steel, considering the phase diagram, and then we will move on to the cast irons and brass and bronze microstructures, which are the common engineering materials, before we get into ternary phase diagram. Thank you very much.